went along, and as I looked and thought about what I might put it on an exam, I thought, well, maybe I should tell you about these things so you're not surprised. And so,
Who is the exam?
let me try to figure out where we are,
Oh, no, those are
where I
just
am, what am I doing? This is sort of an exam review, but I can't find that. There.
Oh, you said it was going to come.
I tried to pull a few things together in order to emphasize what I think is important and what the overall arching ideas are.
Good.
And I just brought along a bunch of examples as well,
Even better.
and my notes on the homework,
That's also good.
and I hope all my lecture notes. So, review. There are a few key elements of mathematics that I want to be sure that you have good mastery of. One of them at this point is not component notation. Right? That was something to practice with initially. And if you solve problems using component notation, that's fine. So, I'm not against you doing it. It's just that I won't give you a problem in which you're required to solve something, to show a solution using a component notation, because I hate reading it. But vector arithmetic, divergence and curl, I'll sort of come back to that. And the properties of the delta function are fair game. So as far as math is concerned, let me just emphasize, and then I'll come back, maybe board by board, as I think of things. So there are some things that you just have to bite the bullet and remember the math. And div grad curl in 3 coordinate systems. And then what I mentioned was the properties of the delta function. And by that I mean delta of x and delta ij. All right. Then we went on to, and this is a key idea that leads to everything. Oh, no, I'm not done with math yet. You should be able to do volume, area, and line integrals. Integrals in the 3 coordinate systems. So that's math for math's sake. I wrote Maxwell's equations here, but I'm going to skip them for the moment. We dealt with concepts related to Coulomb's law. And I used Coulomb's law, actually, as a general phrase to basically describe the properties of the electric field. And the electric field due to a static point charge. So, oops. Electric field due to a collection of charges is sum over all the charges in the system that's the position of measurement R, and I will cube this because then I'm going to multiply by that, okay? So that's what I mean by Coulomb's law and the integral form as well, where we understood that in Cartesian coordinates, r minus rj is x minus xj I plus y minus yj j plus z minus cj k in full coordinate system, and the magnitude is just these squared, take this, add it up and take the square root. And you could easily generalize to the integral over a charge distribution by making this a sum over the volume that includes the charge density, everything else remains the same. Integrating over all the positions of all of the charges, right? There are some consequences of this that are very useful and very important, right? One of them is that the curl of the electric field from any, if the electric field obeys Coulomb's law, right, then in the sort of generalized sense, Coulomb's law is actually Q1, Q2 over R squared, right? But what I'm talking about is the field that you think of when you talk about Coulomb's law, right? The curl of that electric field is 0. That's really important and really useful to us. We'll use it in boundary condition problems. So when we're actually solving for the electric field in various situations, we'll be using that observation. But it also leads to another result, which is that because the curl is 0 and because Coulomb's law, this expression for the electric field leads to the divergence of the electric field is equal to 4 pi charge density. Then, all of these combined leads to, well, this leads to the observation that there must be a scalar potential, which we're going to write like this, whose gradient gives us the electric field. And these two things together give us del squared V is equal to 4 pi, probably a minus sign, but I'm not sure. Okay, and these two observations, which again just come from looking at the form, the 1 over r squared form of the electric field, in fact, the field points out from the charges, leads to these additional useful relationships, which are that at an interface, the electric field on one side of the interface minus the electric field on the other side of the interface dotted into the normal yields the charge density at that interface. And this leads to the electric field on one side of the interface minus the electric field on the other side of the interface crossed into the normal. So if I have an interface, then this relationship tells me the relationship between the electric fields on one side and the other side of the interface perpendicular. So this one's the perpendicular relationship. And this one is the parallel to the interface. So I have electric field, so I could have, that's the normal. And then I would write E1, E2, perpendicular like so, and parallel to the interface P1 parallel, P2 parallel. This one is the parallel condition. Okay? This potential here has certain form and certain properties. The one that goes along with these that I've written here is that the potential is continuous. The electric field is not necessarily if there's surface charge, but even if I've got a sheet of surface charge, the potential is a continuous function of R, right? That means that at an interface, the potential on one side is equal to the potential on the other side of the interface. This sort of combination here, plus any other boundary conditions that we explicitly write down, are what's going to allow us to solve for the potential under a wide range of possible boundary conditions. I'll write the integral form here while I'm at it, which is this. I'm not doing things completely consistently here, so let me write the integral form of this, which is that, oops, the potential difference between 2 points is equal to the integral A to B of the path integral. And this one I might as well write out the integral form of as well, which is that the integral of the electric field passing through a closed surface is equal to I'm just trying to remember whether there's a 4 pi here or not. Someone tell me.
It's a 4 pi cube. Q enclosed.
4 pi
Integral
cubed
over the whole.
enclosed, which I would write also as 4 pi integral over the enclosed volume of rho.
I
Yes,
think you missed the minus sign, the potential contribution.
there for sure. Is that the only one you're referring to? Okay, good. Thank you. All right. This potential here is a scalar, and it has some properties that are useful to us. One is that it's continuous, right? 2, you should just keep this in mind. This is not so much a property as just a reminder. It must be measured with respect to somewhere. Whenever we talk about potential, we're always talking about potential with respect to something. It is the potential with respect, electric potential at some point, with respect to the electric potential at infinity, or the electric potential at 0, usually, or the electric potential at some grounded surface. But we're defining where we're measuring the potential with respect to, and the signs and everything else that comes out of that always has to do with measuring with respect to what. And again, if we have a finite charge distribution, then usually we measure the potential with respect to infinity, but not always. And then what applies to both the electric field and the potential is the idea, I've already written it out over here, that if we want to know the potential function for many charges or for various distributions of charge, we can solve for the potential for one distribution of charge, solve for the potential of the other distribution of charge, and then just add the two. Okay? And that actually is something that makes some solving of some problems much easier. We haven't practiced that, but I'll give you an example in a couple of minutes. And uniqueness. Once you've found the potential that satisfies the boundary conditions and Laplace's equation, you have found the potential. Which brings me to Laplace's equation. I'm just wondering where to put that so that it would be all the way to the right, somewhat organized here. I'll go over there and then erase some stuff over here as we go. Uniqueness, superposition, and the equation that we most frequently end up solving is d squared v is equal to 0. Laplace's equation. Okay, so we really studied very little. Think about it, not that much here. At least I think there wasn't that much here.
It could be
It could be raining.
It might. But that would be a good thing, not a bad thing.
So when we're actually solving, you're asked to solve a problem, what we're almost always really interested in are the fields. And in quantum mechanics, you want to know about the fields. Sometimes you want to know about the potentials, but frequently you need to know about the fields. In mechanics, you need to know the forces on objects and or the potential. So we're frequently looking to solve for the field. And when we wish to do that, when you're posed with a given situation, you have a wide choice of approaches to solving that problem, to solving any given problem. And that's actually the thing that makes this material hard for you, in that you don't have that much experience with problem solving or with certain recognizing situations. So you look at a problem and you don't know whether to address it using which of the approaches that I'm going to mention now you might use, right? So let me start out. I really don't want to erase anything. So just erase all and create more boards. I think downstairs there's actually, we have sliding boards, so there are like 9 boards. I really like that, but I don't have that.
You can do what Fermat did.
Erase the map.
Right in the margins. Right in the margins.
Erase
Yeah.
the map.
It's okay.
Probably not used.
But we need the map. You should
Erase
look,
the map. I'll go back and erase the map in a minute, all right? But I'm going to continue.
you should try and get the
over here.
downstairs room.
So I guess, the question that you should ask yourself when you're being asked to solve for the field in a given problem is, first, is the charge density known? If the charge distribution is known, then it's likely that you're going to want to solve this problem by direct summation or direct integration. Right? There's one set of circumstances where you wouldn't necessarily do this, but if the charge density is known, you find the electric field by, I'll write it like this, summation, right, of where the charges are. You might have to integrate, maybe not. Possibly, you'd find that it's easier to get the potential by summation. And then take the gradient of that potential. Sometimes that's easier. Figuring out which one, under which case it's easier or more straightforward, that's sort of up to you. And you can get yourself into a lot of trouble by choosing the wrong approach. Right? Not a lot of trouble, just a lower grade than the other way. So is the charge distribution known? There's one other way to find the electric field, which is use Gauss's law. Right? The integral form of Gauss's law is the easiest one. But this is really only of use under cases of high symmetry. You have to be able to draw a surface over which the electric field is either a constant and always normal, or the flux through the surface is zero because the electric field is parallel to it, or zero. If you can't do that for a given problem, and for every surface that you're going to make your Gaussian surface out of, every subsurface, if you can't get zero or a constant times the area, then you're probably doing it wrong, and you shouldn't use Gauss's law, right? But there are a lot of special cases where Gauss's law there are a few special cases where Gauss's law is useful. Spherically symmetric distributions, linear and coaxially symmetric distributions, where the azimuthal, you've got complete azimuthal symmetry for linear distribution, and
Infinite curvy linear.
points. What did you say?
Nothing.
Okay. And then sometimes we give you a tricky problem where we just ask you to find out how much charge there is. But you can't find the electric field unless you've got that very high symmetry that you can take advantage of. So that's the first question. Is the charge density known? If not, if it is, integrate somehow, one way or another. Right? If not, is potential known on some surfaces enough to define the region, right? If the potential is known, and I actually have to confess that I haven't thought that much about how much information you have to be given in order to solve a particular problem, right? Normally, in the problems that we've solved, you've needed 2 boundary conditions for each axis in the problem. So I'm going to say 2 times the dimensionality of the problem, all right? But sometimes it might turn out, because you've got symmetry, for example, spherical symmetry, that you only need to know the potential at an inner surface and an outer surface, and then you're done, right? But that's because we've actually already eliminated some of the other boundary conditions by telling you that it's constant. Brian?
You need 2 boundary conditions for every degree of freedom.
Yes, for every dimension.
They're not quite the same.
Yeah.
You can be in 3 dimensions but only have 1 degree of freedom.
Oh, I see what you're saying. Okay, good. I'll go with that. All right.
Means you can give us less information on the tests.
Yeah.
Thank you very much, Brian.
You're welcome.
Good. So, is the potential known on the appropriate number of surfaces? Do you have enough boundary conditions as far as the potential is concerned? Right? Then, if that's known, there are a whole variety of approaches that you could take, and it depends upon what tools you're given to a certain extent. That is, that if it's an in-class examination, it's highly unlikely that you're going to be able to use the mean value theorem at anything more than 1 point at the center of a distribution. But I'll put that in here. Which tells you that there are no extrema when, yes, there are no extrema inside the boundary, and that the value at the center of a spherical surface is equal to the average of the potential on that spherical surface. Right? And then we use it in approximation as you did for your homework. So that's one numerical approach, mean value theory. Another numerical approach is, I should mention this, that when you're given the charge distribution, sometimes it is easier to integrate the differential equation numerically if it's a complicated charge distribution in order to find out what the potential looks like and then solve the field from that. So there are numerical approaches. What else do I want? Yes.
Should be Newton's method.
Go. Solve Laplace's equation in closed form for simple geometries. So I'll say Laplace plus boundary conditions, and sometimes we can do this, or actually almost always we can do this, it just may not be simple, right? Using separation of variables. So I showed you for various geometries what the general solution of Laplace's equation looks like. They're all the same. They're all solutions to Laplace's equation, but which set of solutions you choose depends upon the overall symmetry of the problem, right? That's all that you're doing is selecting what set of functions you're going to expand in based upon the symmetry of the problem, right? So Laplace's solutions to Laplace's equation plus the boundary conditions. Based upon the boundary conditions, you choose which of the solutions to Laplace equation, which of the expressions, representations of the solutions you're going to choose. So I call this expansions in terms of solutions that we know. Okay? And then finally, I think finally, is a trick. Find an easier problem with the same boundary conditions. And what we called this was the method of images. And you've actually worked through just two examples there. There's one other case that you might think about, which is a line of charge above a flat connecting surface, grounded surface. For example, that's not a promise. A line of charge. So what do we study? We've looked at, and I'm going to erase this, a charge sitting above a flat surface,
And then you use Gauss's
grounded
law on
surface.
those lines independently.
And we looked at, for as far as the method of images, a charge near a spherical surface. That's actually all that we've solved, and there are a few other cases that can be solved using hyperboloidal coordinates, and we can even use method of images for dielectric problems. But I consider those to be, I'm talking now about a 1 hour and 50-minute test. Those to be beyond the scope of an examination, of a 2-hour examination.
Good homework problems, though.
They could be, and they might turn up. Okay, although you probably found that just the point charge with the spherical surface was enough to occupy you for some time. Mean value here, cut that.
Brian, learn arithmetic.
Okay, I'm gonna not give you examples of that because we've worked those over quite a bit in homework, but you should feel free to ask for examples. And now comes the important bit.
That was not important.
There's some fun what to raise first.
The math. The
It's
math
all
can
important.
grow.
Yes. Say that again? You're not. Unfortunately. It's with the grader, and I heard that we were going to get it back today, at least 3 of them. And I did not see it in my mailbox. So I'm sort of hoping that it will appear in my mailbox today sometime, and then you can pick it up tomorrow.